Hello everyone. In this video, we're going to tackle the problem of comparing two vector spaces. And we do this by studying functions that map a vector space V into another vector space W that preserve the operations on the vector spaces. Such functions are called linear transformations. To formally define a linear transformation, let's suppose that we are given with V and W two vector spaces. And suppose that V has operations denoted by the usual plus sign and usual times sign, while W has the operation O plus for vector addition and O times for scalar multiplication. So a linear transformation of V into W is a function L that satisfies the following conditions. First, we have this preservation of vector addition for all U and V in the vector space V. On the left, the image of the sum of vectors U and V under L should be equal to the sum under W of the image under L of U and the image under L of V. So remember, in the left-hand side, we're dealing with vector addition in V, while on the right-hand side, we deal with the vector addition on W. The other condition is that L should preserve scalar multiplications. More precisely, for all U in V and all scalars C, the image under L of the scalar multiple of U by C should be the same as the scalar multiple by C of the image of U under L. The standard function terminology is used for linear transformations. So, for instance, here, V is called the domain of L, and W is called the codomain of the linear transformation L. If the codomain and the domain are the same, so that the function L is mapped from V into V itself, then we call a linear transformation uh, such as that a linear operator on the vector space V. Note that the definition of a linear transformation can be stated in the following manner. So instead of stating these two conditions, we can say that L is a linear transformation of V into W if for every scalars C1, C2, and vectors UV in the domain, this identity holds. Okay, so the image under L of the linear combination of U and V with scalars C1 and C2 is equal to the linear combination in W, okay, of L of U and L of V with scalars C sub 1 and C sub 2. So please note that here in the right-hand side, uh, we perform operations. First, we take the scalar multiple of these L of U by C1, and then take the scalar multiple of L of V by C2 in W, and then you add the results under the vector addition operation in W. In this video and in the succeeding videos, unless otherwise specified, when V is Rn or when W is on Rn, the vector space will also always be endowed with a standard addition of vectors and scalar multiplication. So here's an illustration. So let's consider the function L mapped from V equals R3 into W equals R2 given by the following expression. So under L, a 3 vector with components x, y, z is mapped to a 2 vector with components x plus y and y minus z. Is this a linear transformation? So let's check. So we have to verify that the two conditions in the definition are satisfied. So for the first one, let's take two vectors from our V, which is R3. So let's say x1, y1, z1, and x2, y2, z2. So we take the sum of these two and let's compute the image under L of this sum. So we first perform addition. Okay, so L of this sum is equal to L of this 3 vector whose components are x1 plus x2, y1 plus y2, and z1 plus z2. Okay, so this is now in the form of this guy with x equal to x1 plus x2, y equals y1 plus y2, z equals z1 plus z2. So we apply the definition of L. So under L, we should write the two vector whose first component is the sum of the first and second components of the given 3 vector. The second component is the difference, no, of the third component from the second component. So this expression here should be equal to the two vector with entries as shown. Okay, so this is the sum in the first component. We have the sum of the first and second components. In the second component, we have the difference of the third component from the second component. So our goal is to show or check whether or not this is equal to L of x1, y1 plus z. Again, L of x1, y1, z1 plus L of x2, y2, z2. So we just manipulate, no, these two vector. What we do is we combine all terms with subscript 1 and do the same for all terms with subscript 2. Okay, so x1 plus y1 plus x2 plus y2. Here, we take y1 minus z1 plus y2 minus z2. And that can be written as a sum of two vectors. Okay, the first vector with components x1 plus y1 and y1 minus z1. The second with x2 plus y2, y2 minus z2. But observe that here, this two vector is of this form with x equal to x1, y equals y1, z equals z1. And similarly, this two vector is of this form with x equal to x2, y equals y2, z equals z2. Okay, so the definition of L allows us to write each term as L of x1, y1, z1 for this guy, and L of x2, y2, z2 for this guy. So we see that the first condition in the definition of a linear transformation is satisfied. So now let's check if the second condition is satisfied. And that is the condition with respect to scalar multiplication. So consider a scalar C and a 3 vector in our domain. So we have to compute L of the scalar multiple of xyz by C. So before we proceed, we first perform this scalar multiplication. So the image of this under L can be written as L of this 3 vector with components Cx, Cy, Cz. So at this point, we apply the definition of L. So recall that L maps this 3 vector, no, into a 2 vector whose first component is the sum of the first and second components, and the second component is the difference of the third component from the second. Okay, so observe that in this vector, each term has a C. So we can factor out that C. We can write this as the scalar multiple of the vector x plus y, y minus z by C. And applying the definition of L, okay, we see that L of C xyz equals C times L of xyz. So the second condition is satisfied. Okay, both conditions are satisfied. And we conclude that L is a linear transformation of R3 into R2.